Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, you know that based on industrial applications, there are different types of heat exchangers. We are planning to analyze a series of different types of cross-flow heat exchangers in consecutive videos. After that, we'll go for comparative study and performance analysis of those heat exchangers. Today I'll show modeling and analysis of one cross-flow heat exchangers with circular profile. So without wasting time, let us start modeling. We start modeling from part and we'll select right plane for starting that model. Right plane normal to. We start with sketch and initially we draw one rectangle. Next to that we can provide some lines to provide the base support. You can do the same thing on the other side also. Now we can provide some relations to have this rectangle to be square. So select this side and this side. Both these sides should be equal. So we are putting relation to make these two lines equal. Again down also we want to make the same thing, like this line should be equal with this line. Let us make the relation equal. Go and check. Again this vertical heights also. Equal. Next to that we can provide smart dimension to this one. Smart dimension, this one will be 2000 millimeter and base, this one should be 200 and this one also 200. Now we can cut some unwanted entities with trim entities. Let us cut this part. Done. Go and check. Now we'll use offset entities to make a boundary. So for that we have to select the lines, all lines selected. Now offset entities. We want to offset this one by 25 mm outside. Done. Green check. This is the sheet metal that will be utilized for making the cross flow heat exchanger. Next to that we have to provide the circular pipes. So circle. Now next to that we can provide smart dimension to this one. Let us make the internal diameter as 100 mm and you can put some smart dimension that from this side it will be having a distance of 100 mm and from bottom also it will be having the distance of 100 mm. Okay, done. We have to make the outer diameter of this pipe, so we'll select this circle and offset entities by 5 mm. Go and check. So we have provided one pipe of internal diameter 100 mm and thickness 5 mm. Next to that we have to provide a series of circles inside this cross flow heat exchanger using linear sketch pattern. So starting with linear sketch pattern, we want to provide 15 numbers of these circular patterns at a distance of 125 mm away. Again in y direction also we have to do the same thing. Along y direction we have to make 15 numbers of circular patterns and the distance between them will be 125 mm. Next to that we can select that profile. Selected. Now the direction can be changed from here. Done. Perfect. Green check. Initial drawing is ready. Now we have to provide a thickness of this one. Let us select the complete drawing and we'll provide a thickness of 5025 mm. That will be through extrude mouse base. From middle plane we can provide it extrude depth of 5025 mm. Green check. It is done. You can see here the pipes are actually floating right now. So for this one we have to provide some support for these pipes, right? So we can provide support for this pipe with the form of baffles. At the same time we have to provide support from front and back side also, right? Initially we'll provide support from the front and back side. So for that what you have to do is, let us select that surface and we want to provide some sketch on that. Sketch 2 is created. Let us start sketching on that one with normal 2. Let us start some lines. The outline is ready. Next one, we have to provide the circular pattern, that means outer diameter is needed. So starting from circle, and we have to select that OD selected. Next to that, we have to provide linear sketch pattern. Linear sketch pattern, we want to provide 15 numbers of circles at a distance of 125 mm. The direction should be reversed. Again, in the Y direction also we need to do the same thing. 15 numbers of circles to be made in Y direction, and the distance should be 125 mm. Done. You can check it, right? So green check. Now let us select that drawing and that to be extruded in the backward direction. Features extrude boss base, that to be extruded with a depth of 25 mm inside direction. And we want the object to be merged. If we don't merge, in that case the object will be separate. We want to merge that object together with the parent body. Green check. So this is the side view of this one. Now the same thing we can do in the back side by using mirror entities. Starting with mirror face plane, it will be definitely right plane. And as it is merged body, so we have to select the features to mirror. This is the features selected. Green check. Let us see the back side. Yeah, it is done perfectly. It is merged together with the parent body. Okay, right. Next what we have to do is we have to provide some space at the exit location, that will be the output of fluid. We can put some space at this location. So let us select that object and we can start some drawing. Sketch 3 is initiated, normal 2. Let us draw some lines to get the boundary of this one. We can do this one using convert entities also. Let us sketch the boundary of this object. This is done. Next to that, you can select that boundary and we can provide some offset entities. An offset entity will be 25 mm. It will be inside. Done. We have offset this boundary inside by 25 mm. Next to that, we can provide a extrusion depth to this profile. It will come from features extrude boss base, and extrusion depth we want 500 mm. In this case, we don't want to make this body to be merged with the parent body, so uncheck the merge results. You can see by rotating this one. So this is the space for output. Okay, green check. Backside also we have to put the same thing, so we can do it by mirror. First plane will be definitely right plane, and this is, as this is a separate entity, so we have to select the bodies to mirror, and you can select the body from solid bodies. This is the body selected. Green check. Done. So this is the entry location of cold fluid, and this is the exit location, and from this side we will be providing hot flue gases, right? Okay. Next to that, we have to put some kind of baffles, because the pipes should be having some kind of support from mid side also, so we have to put some baffles. For providing baffles, what we'll do is initially we'll select the right plane, and on the right plane we have to provide the baffle. Right, select the right plane, sketch, then you can select that sketch, convert entities. We have made one sketch on the right plane, that to be modified a little bit. Trim entities, some unwanted lines. We are modifying that line with some specific aim. Let us make some vertical lines. Done. Same thing to be done with the other side. We can provide smart dimension to this new drawing. This dimension will be 75 millimeter. The same dimension will be behind the left side also, 75 millimeter. Now we can trim out unwanted entities. This is the profile. You can rotate little bit to see the profile. Now the thing is, like, we have modified this one because we want to provide some kind of gap at the inlet of hot flue gases, because hot flue gas will be moving in this direction. Again, we don't want to provide any kind of restriction in the movement of hot flue gas. It can move this direction also, right? Okay, so that we provided an extrusion depth of 25 millimeter. So features: extrude boss base, and that to be extruded from the mid plane with a depth of 25 millimeter. And we don't want to merge these results. This baffle we want to be separate entity. So uncheck the merge results, green check. So the first baffle is made. If you want to see this one, we can have a transparent model view. We can make the model completely transparent and see the results, or we can cut it from top plane. So this is the baffles, right? This is the position of baffles, right? So we have provided some gap, that means hot flue gas can flow. We don't want to provide any kind of restriction to the movement of hot flue gases. So this one we have made little bit different. Let us make the model transparent. Now the model is transparent. We can see the baffles. Next to that, we have to provide two more baffles at front side and back side. We can do this one using linear pattern. Direction is wanted. You can select any side for the providing direction. It will be provided in the front direction at a distance of 1250 millimeter. Let us provide that profile as body. Let us select that body from here. Let us select that object. Object is selected. Green check. Now the same thing to be provided in the back side also. We can repeat the same thing like linear pattern. We have to put the direction. Now the direction will be back side. We can change the direction from here. Done. And the distance should be 1250 millimeter. Let us select that body to be patterned in the backside. You can select the body from here. Done. Green check. So our model is almost ready. Next to that, you have to provide some leads at the front and back side. That will be started from here. Tools, create leads. You have to select the surfaces for providing leads. One lead is provided. Now the back side also to provide the same lead. Both the leads have been provided. Green check. So our model is ready. To understand the geometry properly, we can cut that object from top plane and view the different fluid subdomains. Cold fluid will be passing from this one and it will pass through these pipes. Cold fluid will be passing from these pipes. And hot flue gases will be provided from this one, right? So we'll have output at this surface by the same time at this surface, right? Okay, fine. Now let us start analyzing. Before analyzing, we have to save this model. Let us save it, and now CFD environment will be created with the wizard. We're starting with wizard. Default name of the project we are keeping as project 1. Next, unit system we are keeping as SI system as default 1. We can create our predefined system also, but in this case we are following to standard SI system, and your temperature will be in degrees Celsius as usual. Next to that, it will be an internal analysis, and uncheck the exclude cavities without flow conditions. It will be heat conduction in solids. By the same time, gravity will be involved, and the direction of gravity will be Y. So along Y direction it will be minus 9.81 meter per second square. And along Z direction it will be 0. Next, gases. Default gas will be air. That means hot flue gas will be passing from side walls, and from the pipes we will be providing cold liquid, and liquid will consider as water. To have selected two different fluids, air and water. Next to that, the material for this cross flow heat exchanger, it will be alloys. We are considering stainless steel 321 as the material for this cross flow heat exchanger. Next to that, default outer wall thermal conditions and roughness we are considering. Next, temperature it will be 20 degrees centigrade, and solid parameters also it will be 20 degrees centigrade. Let us finish this. You can see this is the computational domain. Let us hide this. Next to that, we have to provide two different fluid subdomains, because we will provide cold water from this side, and from the side walls we will be providing hot air at a specific rate. For providing fluid subdomains, it is suggested to have a segmented view of this model, so we'll cut it from top plane. Green check. Let us provide the fluid domains. Insert fluid subdomain. Initially we want to provide cold water at specific rate, so we'll select liquid from here. It will be water at 20 degrees centigrade. We'll be passing from this side. This is the fluid subdomain for cold water. Green check. Next to that, you have to provide fluid subdomain for hot flue gases. So we can rotate this one little bit to have a better location. Now fluid subdomains, insert fluid subdomain. It will be air, and we want to provide air at a specific rate, and the temperature will be 200 degrees centigrade. We are providing hot air from side walls. You can see the domain. So this is the domain for hot air. This will be passing from side walls, and inside you can see these are the baffles. 3 baffles we have provided, and from front side also you can see these are the domain for cold water. From these subdomains we can understand that the volume of hot air will be much more than that of cold water. That means it will provide sufficient amount of heat to cold water. Okay, so green check. Next to that you have to provide boundary conditions. We are planning to provide same mass flow rate from both the sides. Boundary conditions, insert boundary condition. We want to provide water at a rate of 1 kg per second from the inlet locations. It will be water thermodynamic parameters. It will be 20 degrees centigrade water from this side, and the mass flow rate will be 1 kg per second. Go and check. One boundary condition is applied. Now another one needed, so we can rotate this one a little bit to provide hot flue gas from this side. Boundary conditions, insert boundary condition. It will be here at a rate of 1 kg per second from side walls. Green check. Next to that we have to provide another boundary condition, that means atmospheric pressure at the exit location. So boundary conditions, insert boundary condition. It will be atmospheric pressure at the exit location. Selected. Green check. All the boundary conditions have been applied properly. Next to that we can select some goals. We want to have 2 goals only, that means average temperature fluid at the 2 different exit locations, exit of cold water and exit of hot flue gas. So goals will be surface goals, definitely. Insert surface goals. It will be average temperature of fluid at 2 different entries at the exit of cold water. By the same time we want to have the same thing at the exit of hot flue gas also. This is the exit of hot flue gas, and we want to have separate results for each of them. Create goal for each surface. Green check. This is the fluid one, that means we can rename this one as average temperature of fluid at cold surface. You can say this one as TCO. You can rename this one as TCO. That means cold temperature outlet. And the second one we can represent this one as THO, that means temperature at hot outlet. Next to that, to have the performance analysis, we can create one equation goal by the name of LMTD. So goals, insert an equation goal, and equation goal will be obtained from the defined goal itself. Let us add the goals. We know that LMTD is equal to del T1 minus del T2 divided by ln of del T1 by del T2. Here del T1 is the difference in temperature of hot water inlet minus cold water outlet. So the expression will be hot water inlet is 200 degrees centigrade, we know, so we can provide value from here, 200 minus cold water outlet, these two will be within bracket, minus hot water outlet minus cold water inlet, that is 20 degrees centigrade. Again this one will be within bracket. First one is del T1, second one is del T2. So this one will be divided by the ratio of ln. Again you can provide some bracket for this whole expression divided by ln of this ratio, right? You can take this one in the form of ratio. Again first copy this part and put it here, then you can provide the ratio. Instead of minus sign we can provide this one as a ratio. Green check. Now we can define this one by the name of LMTD. Done. Now another thing we can do for having better results, we can have a better mesh. Edit definition. We can refine the mesh manually. Let us see the refinement level. It is refined up to 1 level. Let us refine this one up to 3 levels. Go and check. Now we can run our analysis. Let us run this. Running with a new calculation. Let us run this. You can see SolidWorks has already started iterations. It is preparing model and mesh generation is going on. Let the iterations move on. Whenever it is finished, we will see the results and go for detailed analysis. The SolidWorks is finished. We can see from the results, LMTD is 74.64 and temperature at the cold exit surface is 27.829 degrees centigrade. Its initial temperature was 20 degrees centigrade, so it has gained a temperature of 7.8 degrees centigrade. Similarly, temperature at the hot air outlet is 43.49 degrees centigrade. That means its temperature has been reduced, a huge amount of reduction in temperature. Its initial temperature was 200 degrees centigrade and finally it has come down to 43.49 degrees centigrade. Let us close this. Now we can see the results from the cut plots and insert cut plots. We want to see temperature distribution, temperature of fluid inside this cross flow heat exchanger. Let us see these things from front view. So let us play this in the form of an animation. Let us rotate this one a little bit. You can see temperature distribution of fluid throughout this cross flow heat exchanger. So initial temperature of hot flue gas was red. It was in the range of 20 degrees centigrade. As it is approaching from this side to that side, its temperature is reducing and it is indicated by the change of color. Similarly, the temperature of cold water, as it is approaching from this side to that side, its temperature is increasing as it is getting heat from hot air from side walls. Let us view these things from other plane. So we'll top this one. Let us clear and hide these things, and we can see temperature distribution from other planes also. Edit definition, you can select a different plane. Let us select that right plane and we want to see temperature of fluid. Let us play these things. Cut plot 1. Okay. You can see the distribution of temperature. It will be better to see from side view. It is clearly understood that hot flue gas is passing from side walls, that is indicated by red color. As it is approaching from left to right, its temperature is reducing. Similarly, you can see color distribution. If you rotate this one a little bit, you can see the change of color for cold water. Cold water, as coming from this side to that side, it is gaining some amount of heat. Let us clear and hide. Next to that, we want to see surface plots. Insert surface plots, temperature distribution through all faces. Grain check. Let us see these things. You see here the red color indicated that temperature at this surface is 200 degrees centigrade, and as it is approaching from this side to that side, its color is changing. That means temperature is also reducing. And here also we can see the temperature of cold water is also increasing. Initially it was 20 degrees centigrade, and finally whenever it is coming at this level, its temperature is in the range of 50 to 70 degrees centigrade, indicated by provided color. Let us rotate these things, and you can see the back side also. Back side, you can see the color is blue. That means temperature at the back side is in the range of 29 to 72 degrees centigrade, right? Let us clear and hide these things. Next to that, we want to see dynamics of flow particles. For that, we can cut this one from top 10. We want to see dynamics of flow particles. So flow trajectories, insert flow trajectories. Instead of 20 numbers of particles, we want to have this one to be 100 numbers. And instead of pipes, we want to see in the form of arrows only. Let us select the faces, this face, and by the same time we have to select some other face also. Two faces selected. We want to have the dynamics of flow particles from these two surfaces. Green check. Let us play these things. It will be better if we make the particles very small. Let us clear and hide and edit these things. Let us play these things. You can see the dynamics of flow particles, how hot flue gas is passing from side walls and it is moving across the tubes. As it is getting across the tubes, its temperature is reducing. By the same time, as cold water is passing from this side to that side, its temperature is increasing as it is getting heat from hot flue gases. Okay. Let us clear and hide these things. Next to that, we want to see results from gold plots, which one we have already seen before. All the goals. Select all the goals. Show. We have already seen all these results. We want to see these things in the form of graphs. Let us see these things from history. We can see that after 83 numbers of iterations, temperature of cold fluid, that means temperature of cold water, is increased to 27.8 degrees centigrade. That means we can have a gain in temperature of 7 degrees centigrade. Similarly, for hot water side, you see the final temperature of hot water. Initially at the hot water surface, its temperature was approximately 20 degrees centigrade, and after 83 numbers of iterations, temperature at the exit surface of hot water is 83 degrees centigrade. That means we got a huge reduction in temperature of hot air, and we got the LM3D value finally at 74. Let us close these things. This is the first CFD analysis of cross flow heat exchanger in our series of consecutive heat transfer analysis. Next to that, we will go for another type of cross flow heat exchanger, and finally, after getting all this analysis, we'll have a comparative study and performance analysis. Okay. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.